Okay, so let's unpack this. I mean, think about when you open up a brand new laptop, right?
Oh, yeah, it's just a pristine experience.
Exactly. The screen lights up and everything looks, exactly like a polished mirror.
Very clean, very sanitized.
Right. You've got this beautifully centered taskbar, a super smooth background image, and a search bar that it just waits for your command. It feels entirely frictionless.
It does. It feels like magic to most people.
But the reality is, beneath that really beautifully manicured user interface is a sprawling, just chaotic metropolis built on, more than 30 years of legacy code?
Yeah, at least 30 years. It's wild when you really look at it.
So today, for our deep dive, we are basically ripping up the floorboards of the Windows operating system to show you the engine room.
I love that analogy. We're bringing out the digital crowbars today.
We absolutely are. And to do this, we are using a highly detailed CompTIA A+ certification module as our architectural blueprint, specifically the module on configuring Windows.
Which is incredibly dense material, by the way.
Oh, it's super dense. But just to be clear, we aren't doing this to, help you pass a multiple choice IT test.
Right. That's not the goal here at all.
The mission here is to understand the mechanics of the machine that you stare at every single day. We want to know exactly why it behaves the way it does.
From the pixels on the screen down to the raw electricity flowing through the motherboard.
Exactly. Because, you look at the source material and it's just this ultimate exercise in digital archaeology.
It really is. When you look at a modern operating system, you have to realize you aren't just looking at a static piece of software.
Oh, no, not at all.
You're looking at a living, breathing ecosystem, one that has been forced to adapt to 3 decades of, changing human behavior, hardware revolutions, and just massive corporate demands.
Right, because it has to serve so many different masters at once.
Exactly. It's a high-wire act of engineering. The system has to look cutting-edge and consumer-friendly on the surface for, someone just buying a laptop at Best Buy. But simultaneously, it has to maintain the deep industrial plumbing required to run like a 20-year-old database for a multinational bank.
Which is insane to think about. That tension between the new paint and the old foundation, it's everywhere. Especially when we look at how we physically interact with the machine.
Oh, absolutely. The visual evolution is fascinating.
Yeah, if we track the visual evolution detailed in our blueprint here, it reads like the history of human-computer psychology.
It really does. Let's go back to 1993.
Oh, man. Windows for Workgroups 3.11?
And Windows NP 3.1.
Right. The interface back then was just, flat, gray, pixelated boxes. You had the program manager.
Which, to be fair, was revolutionary at the time.
Oh, sure, because it rescued us from the pure text-based command line of MS-DOS.
Right. Nobody wanted to just type commands to launch a word processor.
No, exactly.
Yeah.
But mechanically, it was still incredibly rigid. The operating system wasn't even truly in charge of the hardware yet, right?
No, not at all. It was basically just a graphical shell running on top of DOS.
A pretty face for a very old engine.
Yeah. The graphical elements, what we call the GUI, or graphical user interface, were basically just floating islands of text and icons.
Loading islands, I like that.
And the mental load on the user was massive because you had to keep track of where everything was manually. There was no unified anchor on the screen.
Right. If you opened too many windows, you literally lost track of what applications were running.
They would just stack on top of each other into infinity. You'd lose your spreadsheet behind your calculator.
Which is what makes 1995 such a monumental paradigm shift, Windows 95.
A huge turning point.
It introduced the Start menu and the taskbar. And from a cognitive design standpoint, this was just brilliant.
It solved so many psychological problems for the user.
Yeah, because the taskbar finally gave us special memory. It gave the user an anchor at the bottom of the screen to show exactly what background processes were active.
Which completely prevented that window stacking chaos we just talked about.
Exactly. And then the Start menu provided a hierarchical map of every tool available. It solved the 2 biggest problems in computing. What do I have and what am I doing right now?
And the mechanics behind that shift were equally profound. It wasn't just a visual upgrade. Behind the scenes, the OS transitioned to preemptive multitasking.
Okay, break that down for us. What does that mean?
So before this, in the Windows 3.1 days, applications had to voluntarily hand control of the processor back to the operating system.
That sounds like a terrible idea.
It was. It was a system called cooperative multitasking. So if a poorly written app decided to hog the CPU or just froze up,
Your entire computer froze.
everything stopped. You had to pull the plug or hit the reset button. But with Windows 95, the kernel finally took on the role of an absolute dictator.
I love that. The kernel is a dictator.
It really was. It could forcefully interrupt an application, slice up the CPU time, and ensure that the mouse kept moving and the taskbar kept updating, even if a background program crashed.
So the interface felt fluid because the kernel was finally enforcing traffic laws.
Huh. Exactly. It took away the trust from the applications and gave it to the system.
And that foundation, the taskbar and the start menu, was so successful that we're still using it 30 years later.
It's the standard. It's how we think about computing.
But the aesthetic layers built on top of it have gone through some wild mood swings over the years.
Oh, definitely.
I mean, we hit Windows Vista and Windows 7, where Microsoft introduced the desktop window manager.
Right, the Aero Glass era.
Yeah, suddenly windows weren't just flat pixels anymore. They were being rendered by the graphics card as 3D objects with glassy, translucent borders.
The OS was using hardware acceleration just to draw the desktop. It was very resource heavy.
And then, after all that success with Windows 7, Microsoft threw a massive curveball with Windows 8.1.
The tile era. Oh boy.
From an engineering and design perspective, the blueprint notes that this was just a fascinating miscalculation.
It really was. I mean, Microsoft saw the rise of the iPhone and the iPad, and they basically panicked.
They assumed the era of the mouse and keyboard was completely dead.
Right. They assumed all screens from then on would be touchscreens. So they just ripped out the traditional start menu entirely.
And replaced it with a massive, full-screen grid of colorful, live updating tiles.
Designed specifically for thumbs and index fingers, not for a precise mouse cursor.
But they completely misjudged how deeply entrenched the traditional workflow actually was.
Totally. People sitting at dual monitor setups in corporate cubicles using a mouse and keyboard, they didn't want to swipe across a massive grid.
No, they wanted precision. They wanted a dense list of text.
Exactly. So we saw the retreat. Windows 10 brought the traditional desktop back.
Right. The start menu returned to the bottom left, the taskbar icons aligned to the left, and the system tray nested safely back on the right.
It was a massive admission that the mouse was here to stay.
But, and I think this is so funny, they kept the underlying code that powered those tiles. They just shoved it back into the traditional start menu shape.
Yeah, that's the nature of this operating system. Code is rarely ever deleted. It is simply repurposed or, buried a layer deeper.
Which brings us to Windows 11 today, which is what the CompTIA A material really focuses on.
Right, the modern standard.
So in Windows 11, the default setting actually aligns the taskbar icons to the center of the screen, kind of mimicking a smartphone dock or a Mac environment.
They completely dropped the live tiles, too, for a much simpler pinned app aesthetic.
It's highly sanitized, heavily centralized, and very sleek.
Yeah.
But, and this is where we really start digging into the blueprint, beneath that sleekness, modern Windows has a bizarre split personality.
Yes. When it comes to actually configuring the system, it has two brains.
The modern settings app versus the legacy control panel.
This is where the archaeology really becomes apparent to the everyday user.
Okay, let's look at the mechanics of this. On the surface, you have Windows settings. This is the modern, touch-friendly interface built on Microsoft's newer Universal Windows Platform, or UWP.
Right, it pops up when you hit the gear icon.
Exactly. It's organized by intuitive, broad categories like system, devices, network, and privacy. And in Windows 11, they completely dropped the old homepage approach.
Yeah, in favor of a persistent, menu-based navigation pane on the left side.
It's highly legible. Honestly, it feels like navigating a modern web app. If you want to change your wallpaper or connect a Bluetooth mouse, you do it here, and it takes 2 seconds.
And mechanically, it is entirely sandboxed and safe. The underlying code of the modern settings app is explicitly designed to prevent you from doing structural damage to the system.
But if you dig just a little deeper, you fall through a trapdoor.
You really do.
I mean, you're in this sleek, dark mode, modern interface, and you click a link that says something like, I don't know, advanced adapter options. Suddenly, a small, gray, boxy window pops up. It has tiny pixelated icons, drop-down menus that look like they belong in 2005, and it functions entirely differently.
You have just entered the legacy control panel.
Yeah. This is where the heavy machinery lists, right? Device manager, administrative tools, internet options, the classic programs and features uninstalled.
All the real power tools.
Now, conceptually, to me, this feels like massive technical debt.
Oh, it absolutely is.
Because Microsoft is one of the wealthiest, most capable engineering organizations on the planet. Why on earth are they forcing the user to navigate a beautifully renovated smart home that is built directly on top of a crumbling, exposed 1990s foundation.
It's a great question.
If I were a software engineer there, my first instinct would be to burn the control panel to the ground and rewrite all those advanced tools directly into the modern settings app. Why hasn't it happened?
Well, because if you burn down the control panel, you burn down global commerce. It's really that simple.
Wait, seriously, global commerce?
Seriously. We have to look at the mechanics of how enterprise environments actually manage thousands of computers simultaneously.
Yeah.
A systems administrator at a hospital or a manufacturing plant, they don't walk around to 5,000 individual computers and click pretty toggles in the settings app.
Right, that would take years.
Exactly. They write automated deployment scripts. They use PowerShell and Windows Management Instrumentation WMI to talk directly to the operating system's registry. So they are hooking directly into the architecture of those legacy tools.
Precisely. Those older control panel applets, which mechanically are technically just specialized DLL files executed by a background process, they have specific, predictable programming hooks.
So third-party software relies on them.
Yes. Third-party enterprise software, complex legacy databases, and literally decades of custom corporate scripts rely on those exact pathways existing exactly where they have always been.
Wow.
So, if Microsoft were to suddenly rewrite the Internet Options panel into a modern UWP app, the registry keys might move, the COM objects would break, and suddenly a hospital's 10-year-old secure intranet portal fails to authenticate on 3,000 machines simultaneously.
Exactly. It would be chaos.
So the technical debt is intentional. It's not a lack of engineering capability. It's practically a hostage situation enforced by the enterprise market.
That is the perfect way to look at it. Microsoft has to build the new bridge while millions of massive freight trucks are still driving on the old one.
That sounds incredibly stressful.
It is. So they are slowly migrating functions one by one. Every major Windows update quietly moves a few more toggles from the control panel into the modern settings app.
Very carefully rewriting the APIs so they don't break the underlying enterprise scripts.
Right. It's a slow, agonizing mutation rather than a sudden reinvention.
Okay, so that dual identity, the shitty front-of-house settings for the consumer and the industrial back-of-house control panel for the admin, it isn't just a quirk of visual design.
No, it actually represents the core philosophy of how Windows manages security and boundaries.
Which naturally brings us to the concept of identity. Because before the operating system lets anyone touch that back-of-house machinery, it strictly authenticates who you are and what you're allowed to destroy.
Identity management is the bedrock of system stability, period. An operating system is essentially just a highly complex bouncer. It manages resources, and it has a very strict VIP list.
So let's pull from the blueprint here. When we look at account settings, there are two primary tiers of power, the administrator account and the standard user account. And I always think about this like the keys to a vehicle.
That's a good way to frame it.
Right. Because if you have an administrator account, you own the car. You have the master key. You can drive it. You can open the trunk. You can tear the engine block apart.
And you can completely total the vehicle if you make a mistake.
Exactly. The blueprint states that the administrator has full system-wide control. They can install software that affects every single other user on the machine, they can modify the registry, and they can bypass almost any security restriction.
Which is precisely why running your daily, everyday life on an administrator account is incredibly dangerous.
Because if you click the wrong link...
Exactly. If you accidentally download a piece of malware while you're logged in as an administrator, that malware automatically inherits your master keys.
Oh, right. Because it assumes you wanted to run it.
Right. It can instantly embed itself into the deep system roots, disable your antivirus, and hide from detection because the operating system assumes, well, the boss authorized this.
That is terrifying. Which brings us to the standard user account. This is the valet key.
Yes, the valet key.
If I give my car to a valet, they can turn the ignition, drive it around the block, maybe adjust the radio station. But that valet key, physically, will not open the glove box. And it certainly won't let them pop the hood.
Same with a standard user. They can run applications, browse the web, change their own desktop wallpaper, sure.
But they absolutely cannot install system-wide software or modify protected directories.
Right. So if malware infects a standard user account, the damage is fundamentally quarantined to that specific user's profile. It cannot touch the engine block.
And we actually see the mechanism of this constantly in modern Windows, right? Through User Account Control, or UAC.
UAC is the enforcement mechanism.
Right, because when you're on a standard user account and you try to install a major application, the screen suddenly dims.
It's a very jarring visual effect.
Yeah, the screen dims, and a harsh dialog box pops up demanding an administrator password.
Oh.
And the blueprint points out that this dimming effect isn't just visual flair.
No, it's called the secure desktop. It's highly mechanical.
How does it actually work?
Well, the operating system literally suspends the entire user environment. It switches to a protected, isolated desktop space that third-party applications physically cannot see or interact with.
Wait, why does it need a separate desktop just to show a prompt?
To prevent malicious software from digitally clicking the yes button on your behalf.
Oh, wow.
Right. By moving the prompt to an isolated desktop space, it forces a physical human being with the master keys to verify the action. A script can't reach across that boundary.
That is a brilliant mechanical detail. The OS essentially halts time, pulls you into an interrogation room, and demands to see your credentials before it lets the installation proceed.
Exactly. It's an interrogation room.
But, there's a newer evolution in identity that goes way beyond just local system privileges. Our architecture blueprint points out a massive philosophical shift in how we log in today.
The shift to the cloud.
Right, the difference between a local account and a Microsoft account. Because back in the Windows 7 days, your identity was purely a local account.
Yes. Your username, your password hashes, your desktop configurations, they were stored exclusively on the physical hard drive inside your machine.
In a database called the Security Account Manager, or SAM.
The SAM file, yes.
And if that hard drive died, your identity died with it.
You were physically tethered to the hardware.
But the default push now, especially in Windows 11, is toward the Microsoft account. And the blueprint notes that this fundamentally alters the architecture because it brings cloud integration and multi-device syncing down to the kernel level.
It completely changes the very definition of what a personal computer is.
Because it's not local anymore.
Right. When you log in with a Microsoft account, your identity is authenticated against Microsoft's Entra ID cloud servers, not a local SAM file. Your identity becomes completely decoupled from the silicon sitting on your desk.
It's portable.
Very portable. You can buy a brand new, out-of-the-box laptop, sign in with your email address, and within minutes, the operating system downloads your encrypted BitLocker recovery keys, your Edge browser history, your saved Wi-Fi passwords, even your desktop wallpaper.
So the operating system just becomes a transient vessel. It just molds itself to fit whatever cloud-based identity pours into it.
Exactly. It's incredibly convenient for the user.
It is convenient, but mechanically, it creates a massive perimeter issue, doesn't it?
Oh, absolutely.
Because if my local machine is constantly pulling down my identity from the cloud, it also means it is constantly beaming my local behavior back up to the cloud.
It's a two-way street.
Which requires us to establish very aggressive boundaries. So let's talk about privacy and permissions in the blueprint. How do we configure what this constantly connected operating system and all the apps running on it are actually allowed to see?
This is where the operating system shifts from being a bouncer at the front door to being a surveillance auditor inside the building.
Okay, I like that. So our configuration blueprint maps out exactly how this arbitration happens.
Yeah.
If you go into the privacy and security settings, you find the app permissions dashboard.
Right. This is where you manage specific hardware access for every single piece of software on your machine.
And the blueprint explicitly highlights the big ones: camera, microphone, location, contacts, calendar, and file system.
The high-value targets for any app.
So let's look at the actual mechanics of this. Say I download a free calculator app from the Microsoft Store.
Okay.
And for some reason, it requests access to my microphone. How does the operating system actually enforce a boundary if I say no? Like, does the app just kindly agree not to listen?
Not at all. Apps are ruthless. They don't operate on an honor system. It's handled at a much deeper architectural level.
Okay, explain that.
Modern operating systems use what are called API brokers.
API brokers.
Yes. When an application wants to use the microphone, it cannot write code that directly accesses the physical sound card on your motherboard. The kernel completely forbids it.
It's walled off.
Exactly. Instead, the application has to send a formal request to the Windows API broker. The broker then checks the privacy settings you configured in that menu.
So the broker is the middleman.
Right. And if you toggle the microphone permission to off for that specific calculator app, the broker intercepts the request and sends back a blank audio stream.
Wait, really? It sends a blank stream?
Or simply an error code saying the hardware doesn't exist or that it's currently in use by something else. The app is completely isolated from the physical hardware. It's living in a simulated reality where the microphone simply isn't there.
That is fascinating. The OS is effectively lying to the application to protect the user's privacy.
It's a very noble lie.
But it's not just third-party applications we have to audit, right? We have to audit the operating system itself.
Oh, absolutely. The telemetry data.
Yeah, the blueprint details system-level privacy telemetry. Windows generates massive amounts of data just by running. It generates diagnostic data, things like crash reports, driver conflicts, memory dumps.
All of which gets sent to Microsoft.
Right. And it generates an activity history, which tracks the specific files and apps you open to timeline your workflow. It monitors your clipboard data, meaning everything you copy and paste.
That's a big one people forget about.
And it generates a unique advertising ID to track your behavior and serve personalized ads across the web.
Now, to be fair to the architecture, this telemetry is often the tax we pay for the cloud-integrated convenience we just discussed earlier.
Sure.
Microsoft uses the diagnostic data to identify hardware conflicts and push vital driver updates before your system crashes. But you're right, the sheer volume of data being harvested is staggering.
Which is why the privacy and security menu allows you to throttle it. The blueprint points out that you could disable the advertising ID, you can clear your activity history, and you can reduce diagnostic data down to the absolute bare minimum required for security updates.
And you really should if you care about your footprint.
And speaking of security, right next to the privacy toggles is the Security Hub, Windows Security.
The central nervous system for active defense.
Right. It houses Defender antivirus, which does real-time behavioral analysis on executables. It houses the firewall and network protection and the smart screen filter, which checks web traffic against a cloud-based list of known malicious servers.
It is also the hub for activation.
Oh, activation, which always just sounds like an administrative annoyance, right? Just verifying that you paid for a genuine license.
Most people view it as just a billing check, but it's actually a critical security mechanism.
How so?
Without a mathematically verified, cryptographically signed activation ticket from Microsoft servers, the operating system will eventually restrict functionality. And most importantly, it will cut you off from essential kernel-level security updates.
So if you aren't activated, you aren't patched.
Exactly. You become a massive liability on the network.
Okay, so we've established our identity, and we've negotiated our boundaries with the operating system's internal auditors. But once you are authenticated and protected, the OS has to physically accommodate the human being sitting in front of the monitor. It has to mold its digital outputs to fit the physical realities of your eyes, your ears, and your hands.
And this is where we move from the cold logic of security into the deeply human-centric design of accessibility.
Yeah, the blueprint spends a significant amount of time on the ease of access settings. And historically, accessibility tools were buried deep in obscure submenus, right? They were treated almost as an afterthought.
Oh, for a long time, yes. They were very hard to find.
But today, they are front and center, integrated directly into the core shell of the OS. The blueprint breaks them down into 3 categories of human interaction: vision, hearing, and interaction.
Let's start with vision. It's so much more than just making text bigger.
Yeah, the system doesn't just offer larger fonts. It offers a high contrast mode, which fundamentally alters the rendering of the UI.
Right. It mathematically calculates the borders to make text distinct for people with low vision, completely stripping away the gradients and transparencies that look pretty but ruin legibility.
It also includes narrator, right?
Yes. Narrator is incredible. It's a kernel-level screen reader that intercepts UI text elements before they are even drawn on the screen and translates them into synthesized speech.
And a magnifier that can track the mouse cursor and scale the vector graphics of the display up by hundreds of % without losing sharpness.
These aren't just convenient toggles, they are vital bridges. Without them, a complex visual interface is essentially a brick wall to someone with severe visual impairment.
It's completely inaccessible. But the hearing category, this is where I had a massive aha moment in the blueprint.
Oh, the audio setting.
Yeah. So it lists options for visual alerts. So if a background process throws an error beep, the OS can intercept that audio call and physically flash the active Windows title bar instead.
Which is great for deaf users or noisy environments.
Right. But the most fascinating toggle to me is the mono audio option.
Mono audio. Yes.
Because I've always been an audiophile, right? I just assumed stereo sound, where the audio engineers meticulously mix distinct left and right channels to create a 3-dimensional soundstage. I assume that was just objectively superior.
It gives you depth, sure.
Yeah, it gives you depth. So why would an operating system build a specific system-wide toggle to crush all that hard work and force the audio into a flat mono track?
Well, to understand why, you have to think mechanically about how audio channels work and step outside the assumption of perfect bilateral hearing.
Okay, break it down.
Think about a stereo mix for a popular song. Often, the producer will pan the bass guitar entirely into the left channel and maybe an acoustic guitar entirely into the right channel just to give the vocals room to breathe in the center.
Right, like an old Beatles record. They do that all the time.
Exactly. Now, if a user is deaf or hard of hearing in their right ear and they put on headphones to listen to that stereo track, they aren't just hearing a quieter version of the song.
What are they hearing?
They are literally missing 50% of the data. The acoustic guitar simply does not exist for them. The audio information is being routed to an ear that cannot receive it, and it is permanently lost.
That is wild. The data is just vanishing into thin air.
Precisely. By toggling mono audio in the accessibility settings, the operating system intercepts the audio stream at the driver level before it ever reaches the physical sound card.
Oh, wow.
It takes the mathematical data for the left channel, adds it to the mathematical data for the right channel, sums them together into a single comprehensive audio track, and then pumps that exact same combined track into both the left and right speakers simultaneously.
So it destroys the three-dimensional soundstage, but it guarantees that zero data is lost regardless of which ear the user is relying on.
Exactly. It prioritizes information completeness over aesthetic depth.
And mechanically, that is incredibly useful even for situational constraints. I mean, think about it. If I'm working in a warehouse where safety regulations require me to keep one ear completely open to hear forklifts, I can only wear one earbud.
Right, you can't wear both.
If I'm listening to a podcast where you and I are panned left and right, I would literally only hear my own voice. Mono audio solves that entirely. It forces the system to adapt to the physical constraints of the user.
It is the perfect distillation of what an operating system should do. It acts as a translation layer between the rigid binary of the machine and the fluid reality of the human.
We see that exact same translation layer in the interaction category too. How do we physically tell the machine what to do? The blueprint details the on-screen keyboard for touch interfaces and advanced eye control hardware integrations.
Yes, for ALS patients, eye control is revolutionary.
But the feature that really caught my attention mechanically is sticky keys.
Ah, sticky keys, the feature everyone triggers by accident.
We've all done it. You hold down the shift key for too long while thinking about what to type, and suddenly the computer emits a harsh, interrupting beep, and a dialog box pops up asking if you want to turn on sticky keys. It feels like an error. What is the actual mechanical purpose of this?
It's actually designed to solve a hardware interrupt problem for users with limited manual dexterity, or users who only have the use of one hand.
Okay, how so?
To type a capital letter or execute a keyboard shortcut like Control-Alt-Delete, the traditional keyboard paradigm requires simultaneous chording. You have to physically depress multiple keys at the exact same moment.
Which requires spreading your fingers really wide or using two hands.
Exactly. For someone with motor impairments, holding one key down while reaching for another is physically impossible.
So how does sticky keys fix that?
It intercepts the hardware interrupts at the driver level. When you press the shift key and let go, the keyboard controller normally sends a key up signal to the OS telling it the shift is over.
Right.
Sticky keys catches that key up signal and essentially holds it hostage. It tells the operating system, keep the shift state active in the system's memory until the user presses the next sequential key.
So it translates a simultaneous physical requirement into a sequential set of actions. You press shift, you let go. You press A, you get capital A.
Exactly. The OS is buffering the input state to accommodate the human hand. It's brilliant engineering.
It really is. Beyond accessibility, though, the OS also has to synchronize the human's environment with the rest of the world. The blueprint heavily emphasizes time and language settings.
Yes, which sounds so boring on the surface.
Right. It seems incredibly basic, setting time zones, toggling daylight savings, syncing with a network time protocol, or NTP, server. But mechanically, time synchronization is arguably one of the most critical security features on the machine, isn't it?
It is. Time is the absolute foundation of cryptographic trust.
Explain that. Why is my computer knowing the time matter for security?
When you connect to a secure website, say your bank, your browser, and the bank's server exchange SSL certificates to prove their identity and encrypt the traffic.
Okay.
Those certificates have highly specific cryptographic timestamps. Furthermore, in an enterprise environment using Active Directory, the computers authenticate using a protocol called Kerberos.
Kerberos, right.
Kerberos issues tickets that grant access to network resources. To prevent a hacker from intercepting an old, valid ticket and reusing it later, what's called a replay attack. Kerberos heavily relies on time.
So the ticket has an expiration date.
More like a strict validity window. If your local computer's clock is skewed by even 5 minutes compared to the domain controller's clock, the server will instantly reject your authentication attempt.
Really? Just 5 minutes?
Just 5 minutes. You won't be able to log in, you won't be able to access file shares, and secure websites will throw massive security warnings saying the certificates are invalid.
So when a user travels from, say, New York to London, and they open their laptop at the hotel, and the internet is seemingly broken, the hardware is fine, the network is fine, but the cryptographic math is failing because the local clock hasn't updated its time zone.
Precisely. It's a literal space-time problem.
You go into settings, time and language, force a sync with the NTP server, and suddenly the math aligns and the internet works again.
The operating system has to agree with the global consensus of time, or it is exiled from the secure network.
Wow. Okay, the final sensory configuration the blueprint covers is the display. Under system settings, the OS has to manage the physical real estate of your monitors.
Right. Multiple monitor setups.
If you have a laptop and you plug in an external monitor, you have to configure the relative positioning. Because mechanically, the OS has no idea where that monitor is sitting on your physical desk, does it?
No, it is blind to the physical world. It just receives an extended display identification data package through the HDMI cable.
And what does that package say?
It just says, hello, I am a Dell monitor with a 4K resolution. That's it. The OS defaults to assuming it's an extension to the right.
Right, so if the monitor is physically sitting on the left side of your laptop on the desk,
right,
and you drag your mouse to the left, it will just hit a hard wall.
Exactly. You have to go into display settings and literally drag and drop the logical rectangles to match your physical desk layout.
The OS is creating a virtual spatial map of your hardware. And this is also where the graphics driver negotiates the refresh rates and color calibration profiles, the ICC profiles, to ensure that the red pixel the OS wants to draw is accurately represented as the correct wavelength of red light on the physical LCD panel.
It's a massive amount of translation.
So we've mapped the physical environment, we've configured the displays, the audio summing, the keyboard interrupts, and the cryptographic clocks. We've organized the surface layer of the machine.
But what about the actual stuff?
Exactly.
No.
Where's the data? We need to dive below the interface. Let's move into the map and the territory, File Explorer, and the mechanics of indexing.
We are leaving the decorated rooms of the house and going down into the basement to look at the plumbing, the structural beams, and the raw storage.
The blueprint is very specific about how the File Explorer functions as your viewport into the NTFS file system. And it points out that the vast majority of the hard drive is simply hidden from the user by default.
Yes, for your own protection.
The critical system files, the literal binary code that makes the computer function, live in specific protected directories. Primarily, the Windows folder, where the kernel and drivers live.
Right.
The Program Files folder, where traditional 64-bit applications are installed. And the Users folder, where your local profiles and documents live.
But the blueprint tells us exactly how to bypass these visual restrictions.
It does.
What?
If you go into File Explorer, click the View tab, click Show, and toggle on Hidden Items, suddenly the ghost architecture appears.
It's like turning on a blacklight.
Yeah, you see slightly translucent folders that were previously invisible. Folders like Program Data, which holds system-wide application settings, and App Data, which is nested inside your user profile.
App data is incredibly important for troubleshooting.
Why is that?
It's where modern applications store their cache, their temporary files, and your specific user configurations. If a program is behaving erratically, say Spotify won't load, often a technician will simply navigate into the hidden app data folder and delete the program's configuration folder.
And that fixes it.
Yeah, it forces the app to rebuild its settings from scratch the next time you open it. It's a total reset without having to reinstall the app.
The blueprint also strongly advises using the View tab to show file name extensions. Instead of just seeing an icon called Invoice, you see invoice.txt or invoice.pdf.
This is a massive security point.
Mechanically, why does Microsoft hide file extensions by default? And why is turning them on considered a critical security practice?
Well, Microsoft hides them for aesthetic simplicity and to prevent users from accidentally breaking files.
Breaking them how?
If a user tries to rename document.txt to my letter and accidentally deletes the .txt extension in the process, the operating system immediately loses its file association mapping.
So it doesn't know what the file is anymore.
Right. When they double-click it, the OS doesn't know whether to open Word, Notepad, or Excel, and it throws an error. Hiding the extension prevents that kind of user error.
Okay, that makes sense for usability.
However, from a security standpoint, hiding extensions is a massive vulnerability that relies on social engineering.
How so?
Malware authors know extensions are hidden by default, so they will name a malicious executable file something like financialreport.pdf.exe.
Oh, that's sneaky.
Because the OS hides the true extension, the .exe, the user only sees financialreport.pdf and a fake PDF icon.
They assume it's a safe document.
They double-click it, and they have just executed a virus with their own user privileges. Toggling Show File Name Extensions in File Explorer strips away the disguise. You see the .exe and you instantly know it's a trap.
That is a phenomenal mechanical breakdown of how a usability feature becomes a major security flaw.
It's a constant battle between convenience and security.
But the blueprint points us toward an even deeper layer of hidden architecture. Beyond just showing hidden folders, there's an advanced setting buried in the File Explorer options.
The danger zone.
Yeah. You have to physically uncheck a box that is labeled Hide Protected Operating System Files.
Yeah.
Recommended. And the CompTIA A slide deck includes a massive red warning icon next to this step. It says, be cautious. Modifying protected files can affect system stability.
It's not kidding around.
My question is, why go to such lengths to obscure these files from the administrator? If I bought the machine and I have the master keys, why is the OS actively trying to hide its own engine block from me?
Because a modern operating system is unfathomably complex, and the potential for catastrophic, unrecoverable user error is incredibly high.
What happens if you unhide them?
If you unhide those protected operating system files, you are suddenly looking directly at the raw components of the boot process. You might see a file in the root directory called bootngr, or a cryptically named file deep in the Windows folder like entoskirnl.exe.
Which just looks like keyboard spam to most people.
Exactly. To a user who is frantically trying to free up hard drive space, an ancient-looking file with a weird name might look like useless junk.
So they delete it.
Right. But entoskirnl.exe is the NTOS kernel. It is the absolute beating heart of the operating system.
So what happens if you delete that file or even just rename it by accident?
The next time you restart your computer, the BIOS will hand control over to the bootloader will look for the kernel, it won't find it, and the machine will instantly halt. You will get a permanent blue screen.
The machine is dead.
Completely dead. By hiding these files, the operating system is throwing a heavy tarp over the engine's spinning fan blades. It is protecting the user's data from the user's own curiosity.
Don't touch the fan blades.
I like that.
Now, managing a file system with literally millions of individual files creates a massive logistical problem. Finding them.
Search, the bane of everyone's existence.
The blueprint addresses a universal frustration slow computer searches. We've all been there. You hit the Windows key, you type the name of a document, and you just stare at a loading bar that crawls across the screen for 3 minutes while the hard drive grinds away.
The agonizing full drive scan.
But the blueprint points to the mechanical fix. Indexing options. Let's break down how this actually works. When you run a raw search without an index, what is the computer actually doing?
The operating system's search protocol has to start at sector 0 of your hard drive, pick up every single file, read its name, check it against your search term, put it down, and move to the next one.
It is sequentially checking millions of items.
Yes. It is the equivalent of trying to find every mention of the word kernel in a massive textbook by starting on page 1 and reading every single word until the end of the book. It is a wildly inefficient use of I/O operations.
So to solve this, Windows runs a background service called searchindexer.exe. It acts as a highly efficient obsessive librarian, right?
Exactly. A very busy library.
When your computer is sitting idle, the indexer quietly crawls through the directories you've specified, catalogs the file names, the metadata, and even parses the text inside documents like PDFs and Word files.
It reads the contents too, yes.
It takes all this information and builds an inverted index, essentially a massive, highly optimized SQLite database file hidden deep in the system data.
It builds the index at the back of the book.
Yes. So when you hit the Windows key and type a search term, the OS doesn't even look at the hard drive. It simply queries that SQLite database.
Yeah.
The database instantly returns the exact file path, and the search result appears in milliseconds.
It's brilliant, but The indexer has a massive appetite for CPU and disk resources while it is building that catalog.
Which is why the blueprint tells us exactly how to configure it. You can open indexing options and explicitly add or remove folders.
Because if you plug in a massive 4 terabyte external backup drive filled with decades of old family photos,
The Windows indexer might try to index the entire thing.
and this will cause aggressive disk lashing, your fans will spin up like a jet engine, and your CPU usage will spike, killing your battery life.
So the rule of thumb from the blueprint is fewer indexed locations equals faster indexing and better system performance. You tell the librarian to only catalog the documents in desktop folders and leave the massive backup drives alone.
And the blueprint also includes a critical troubleshooting step here. Sometimes that SQLite database becomes corrupted. Power loss, bad sectors on the drive, or just software bugs can break the catalog.
So if your searches are suddenly taking forever, or if you are staring right at a file on your desktop, but the Windows search bar claims it doesn't exist, the index is broken.
It happens more often than you'd think.
In the indexing options menu, there's an advanced button with a command to rebuild the index. When you click that, the OS deletes the old database entirely and forces the search indexer process to walk the aisles and catalog everything from scratch.
It takes time, maybe a few hours, but it resolves almost all phantom search issues.
Okay, so we've mapped the logical territory of the file system. We've seen the hidden kernel files and the indexing databases, but now it's time to take the ultimate plunge.
The final descent.
We are leaving the software layer entirely and descending to the absolute deepest level of the operating system, where the code physically manipulates the hardware and manages raw electricity. Welcome to the engine room.
This is where we deal with ACPI power states, the mechanics of network packet filtering, and the deep architectural differences between how applications execute.
Let's start with power states. The blueprint outlines how the operating system communicates with the motherboard to manage electricity, using a standard called ACPI, the Advanced Configuration and Power Interface.
It categorizes power consumption into distinct numbered states.
Mechanically, the OS isn't just turning the power supply on or off, is it?
No, it is sending highly specific ACPI commands to the motherboard's firmware to dictate exactly which hardware components receive voltage.
Okay, let's go through them. We have state S0.
S0 is system on, the CPU is fully powered, the display is lit, and everything is active.
And on the other end of the spectrum, we have S5, which is soft off.
That's when you click shut down. The operating system safely closes all files, halts the kernel, and tells the motherboard to cut power to everything except a tiny trickle of voltage monitoring the physical power button on the case.
And then there's G3, which is mechanical off. You physically pulled the plug from the wall.
Right, zero power anywhere.
But the states that confuse users the most are S3 and S4, sleep versus hibernate.
This is a crucial mechanical distinction that fundamentally dictates how your data is preserved.
Let's use an analogy here. I like to imagine your workflow as a physical desk. The physical desk represents your system's RAM, the random access memory.
Okay.
Now, RAM is incredibly fast, but it is volatile memory. It requires a constant, unbroken flow of electricity to retain data. If the voltage drops for even a fraction of a second, every 0 and 1 stored in that memory is instantly wiped clean.
It's gone.
So sleep mode, which is ACPI state S3, is like leaving all your paperwork spread out of your desk and turning off the overhead lights.
The operating system turns off the monitor, spins down the hard drive, and cuts power to the CPU.
But it keeps a continuous trickle of electricity flowing directly to the RAM modules.
Because the RAM is powered, the system remembers exactly where you were.
Right. When you wiggle the mouse, the OS instantly wakes up the CPU, turns on the screen, and you are immediately back to work in 2 seconds. But here's the danger. If you are working on a laptop and it is in S3 sleep, it is still slowly draining the battery to keep that RAM alive.
And if the battery hits 0?
The power to the RAM is cut, the desk is completely wiped clean, any unsaved Word documents or open browser tabs are permanently destroyed.
Which is precisely why Hibernate, or ACPI State S4, was engineered.
Yes. Hibernate is not leaving the papers on the desk. Hibernate is taking the time to carefully pack all those papers into a fireproof filing cabinet.
Mechanically, how does it do that?
When you trigger S4 Hibernate, the operating system takes a literal snapshot of every single megabyte of data currently sitting in the volatile RAM. It takes that massive chunk of data and writes it sequentially to the non-volatile hard drive into a massive hidden system file called hyperfill.nessus.
And a hard drive relies on magnetic platters or flash memory cells. It does not need electricity to remember data.
Exactly. Once that massive hibernate.sys file is safely written to the drive, the operating system alters the bootloader pointer and then sends an ACPI command to cut all power to the motherboard, 0 voltage.
You could physically remove the battery from the laptop.
You could throw the laptop in a closet for a year, put a new battery in, and press the power button.
And what happens?
The BIOS wakes up, looks at the bootloader, and the bootloader says, wait, don't load the kernel from scratch. We are in an S4 state. It reads the hibernate.sys file from the hard drive, copies it directly back into the RAM, and suddenly your desktop appears exactly as you left it a year ago.
It takes significantly longer to wake up because it has to read gigabytes of data from the drive, but it is 100% immune to power loss.
And we're seeing modern evolutions of this, too. The blueprint mentions hybrid sleep, which is used primarily on desktop computers.
Right, because a desktop doesn't have a battery. A power outage during S3 sleep is catastrophic.
So hybrid sleep does both simultaneously. It writes the hibernate.sys file to the hard drive for safety, but it keeps the RAM powered for a quick wake. If the power stays on, it wakes instantly. If a thunderstorm knocks out the power, the RAM dies, but the system just recovers from the hard drive hibernation file instead.
It's the best of both worlds. We also have the highly controversial modern standby, or S0 low power idle.
Oh man, modern standby.
This is Microsoft attempting to make laptops behave like smartphones. When you close the lid, it doesn't truly go to S3 sleep. It stays in a highly throttled S0 state. The screen goes dark, but the network card stays active, and the CPU occasionally wakes up to download emails or perform background updates.
Which is exactly why sometimes you pull a laptop out of your backpack and it is inexplicably burning hot and the battery is completely dead.
The OS decided it was a great time to install a massive Windows update while suffocating inside a nylon bag.
The mechanics of power management are constantly fighting the demands of network connectivity.
They are completely at odds sometimes.
And speaking of network connectivity, a modern machine is essentially useless without the internet, which means it is constantly exposed to hostile traffic. Let's look at the mechanics of the Windows Defender Firewall.
This is critical.
The blueprint breaks the firewall down into inbound rules and outbound rules applied across different network profiles, domain, private, and public. Mechanically, the firewall is doing stateful packet inspection at the kernel level. It is looking at the headers of every single packet of data entering or leaving the physical network interface card.
The inbound rules are easy to understand. It's a security guard at the door.
Right.
If you are sitting on a public Wi-Fi network at an airport, the firewall profile shifts to public. The inbound rules become incredibly strict. If another computer on that airport Wi-Fi tries to send a packet probing your laptop for an open file sharing port, the firewall intercepts the packet, sees that it wasn't requested by your machine, and silently drops it.
It makes your computer effectively invisible to the local network. But the outbound rules are where the real mechanical control lies, and they are so often ignored by users. Outbound rules don't protect you from the outside coming in, they protect you from the inside getting out.
That's a great way to put it.
If you download a questionable piece of freeware, and you install it bypassing UAC because you gave it the administrator keys, the inbound firewall can't save you. The threat is already inside the house.
The call is coming from inside the house.
Exactly. But what if that freeware is actually spyware, designed to quietly package up your keystrokes and transmit them to a remote server?
That is where the outbound rules act as the final failsafe. You can open the Windows Defender Firewall with Advanced Security, which, by the way, is another one of those deep legacy MMC snap-ins in the control panel.
Right.
And you create an explicit outbound rule for that specific application executable. You were telling the kernel, under no circumstances is this specific program allowed to transmit a single packet of data out to the internet.
So even if the malware tries to open a connection, the firewall silently drops the outbound packets at the network stack. It traps the malware in a digital Faraday cage.
It is the ultimate hall monitor.
Now that brings us to the very last topic in our engine room exploration. The application ecosystem itself. We have power, we have a filtered network connection, but what are the actual mechanics of the software we are running?
The software architecture.
The blueprint categorizes modern Windows applications into 3 distinct types based on how they interact with the file system and the registry.
Okay, what's the first one?
First, we have store apps. These are downloaded from the Microsoft Store, built on the UWP architecture. Mechanically, these are incredibly safe because they utilize app container sandboxing.
Right, they run in a heavily restricted integrity level.
They are forbidden from reading the global registry. They cannot write to the Windows folder, and they require absolutely zero administrator privileges to install because they are functionally isolated from the core OS.
If a store app crashes, it crashes inside its padded room. It cannot take down the operating system.
Second, we have user context applications. The Blueprint notes these are incredibly popular right now for tools like Slack, Spotify, or Discord.
Oh yeah, almost all web wrapper apps use this now.
Instead of installing into the protected system-wide program files directory, the installer writes the executable directly into the user's hidden app data folder.
Which we talked about earlier.
Because the user already has full permission to write to their own app data folder, this completely bypasses the need for the UAC administrator prompt. A standard user with a valet key can install their own chat applications without bothering the IT department.
But that application only exists for that specific user. If another person logs into the same computer, they won't even see the program installed.
Which brings us to the third category, traditional desktop programs. These are your heavy legacy installers. They write binaries to program files, they dump global configuration data into program data, and they weave themselves deeply into the system-wide registry hierarchy.
And to do all of this, they absolutely require administrator privileges.
Now, conceptually, based on everything we've discussed today, sandboxes are safe, app data is convenient, and UAC prompts are annoying. If Microsoft has built this highly secure, isolated store app architecture, why do traditional desktop programs still exist? Why hasn't the entire ecosystem moved into the safety of the sandbox?
Because a sandbox, by definition, has high walls. It keeps threats contained, but it severely restricts movement and capability.
So they can't do enough.
Right. The traditional programs still exist because they need deep structural hooks into the operating system kernel to perform heavy lifting.
Like what? Give me an example.
Think about professional virtualization software like VMware, or an advanced video editing suite, or even a kernel-level anti-cheat system for a competitive video game.
Oh, right. Anti-cheat has to run super deep.
These programs cannot function inside a padded room. They need to interact directly with the hardware, they need to allocate raw CPU scheduling, they need bare metal access to the graphics card pipeline, and they need to install specialized driver files into the Windows System 32 directory.
And a safe, isolated UWP sandbox fundamentally denies that level of raw architectural access.
Exactly.
Yeah.
The heavy machinery needs to bypass the API brokers and touch the engine block. That is why traditional programs and the elevated privileges required to install them are not going anywhere anytime soon.
That perfectly explains the mechanical necessity of legacy software. But the Blueprint throws one final, massive architectural curveball that completely redefines what Windows is capable of.
Oh, WSL.
Yeah. We're talking about an application environment that requires deep virtualization hooks, but it isn't running Windows software at all. The Blueprint highlights WSL, the Windows subsystem for Linux.
From an engineering and historical standpoint, this is the most profound technical shift in the modern Windows era.
For decades, Windows and Linux were diametrically opposed philosophies. They were bitter corporate rivals. Linux was open source, server-dominated, command-line heavy. Windows was closed source, desktop-dominated, GI heavy.
They hated each other.
But the Blueprint points out that Windows can now natively run full Linux distributions like Ubuntu or Debian directly inside the Windows environment. You open a terminal window on your Windows desktop, and you are instantly interacting with a raw Linux bash shell, executing Linux binaries as if you were running a native Linux machine.
And to understand how wild this is, we have to look at the mechanics of how Microsoft achieved it. They didn't just write a translation layer. The current iteration, WSL2, actually deploys a lightweight utility virtual machine in the background using Microsoft's Hyper-V hypervisor architecture.
So it's a real virtual machine.
Yes. When you launch Ubuntu inside Windows, the Windows kernel spins up a real Microsoft-compiled Linux kernel running in a highly optimized virtual machine. It uses a specialized protocol to seamlessly bridge the file systems, allowing the Linux kernel to read and write directly to your Windows NTFS hard drive at near-native speeds.
That's crazy.
It dynamically allocates RAM back and forth between Windows and Linux based on what you are doing.
So the operating system isn't just managing its own legacy control panels and modern settings. It has become a hypervisor. It is actively hosting a rival operating system inside its own architecture.
It is the ultimate admission of reality. Microsoft realized that modern software development, web infrastructure, and cloud engineering are completely dominated by Linux tools.
Right, all the web servers run Linux.
Exactly. So rather than forcing developers to buy MacBooks or constantly reboot their machines into a separate Linux partition, Microsoft engineered Windows to be the ultimate host platform. It turns the OS from a closed, proprietary box into an infinitely flexible playground.
It's the Russian nesting doll of operating systems. A Linux kernel running inside a Hyper-V virtual machine, managed by a Windows kernel, configured by a modern settings app layered over a legacy control panel.
It's a beautiful mess.
And that brings us to the end of our architectural blueprint. What a journey this has been. We have peeled back every single layer of the floorboards.
We really went deep today.
We started at the surface, tracing the visual evolution from the cooperative multitasking days of Windows 3.1 through the paradigm shift of the Windows 95 taskbar to the centralized UI of Windows 11. We explored the deep technical debt holding the legacy control panel in place alongside the modern settings app.
We moved into the mechanics of identity, breaking down the secure desktop of user account control and the shift from local SAM databases to cloud-hosted Entra ID accounts. We examined how API brokers enforce our privacy boundaries.
We looked at how the OS physically adapts to the human through accessibility, the brilliant mechanics of summing audio channels to mono and intercepting keyboard interrupts for sticky keys. We navigated the hidden folders of the file system and learned how the squally database of the Windows indexer prevents agonizing hard drive scans.
And we finally descended into the engine room, breaking down the volatile RAM dynamics of ACPI S3 Sleep versus the non-volatile disk writing of S4 Hibernate. We configured kernel-level packet inspection with the firewall and analyzed the deep architectural differences between sandbox store apps and the raw power of hypervisor-driven Linux subsystems.
It is just a staggering amount of engineering designed to hide behind a polished glass screen.
It really gives you an appreciation for the
Yeah.
machine.
So, as we wrap up this incredibly deep dive, I want to toss it over to you for a final conceptual thought. We've looked at the history and the current mechanics, but based on the trajectory outlined in this blueprint, where is this architecture actually heading?
Well, if you look closely at the mechanics we've unpacked today, you see two massive trends accelerating toward each other.
Okay, what are they?
First, we saw how Windows is aggressively tying authentication to Microsoft accounts, pulling your encryption keys, your passwords, and your desktop configurations off the local silicon and storing them in the cloud. Second, we saw with WSL that the local environment is becoming less of a rigid ecosystem and more of a flexible hypervisor, a host platform capable of running entirely different operating systems inside itself.
Right.
So, the conceptual question I leave you with is this. Are we witnessing the slow death of the physical operating system as we know it? We are used to thinking of Windows as a massive block of code permanently installed on a physical hard drive sitting under a physical desk. But as the computing shifts to the cloud and local hardware just becomes a hypervisor, are we rapidly moving toward a future where Windows isn't software you install at all?
Oh, wow.
Will it simply become a personalized, cloud-hosted digital aura? A streaming interface that instantly materializes, complete with all your files and settings, on literally any piece of glass or augmented reality headset you happen to authenticate with anywhere in the world.
A ghost in the machine that follows you everywhere.
Yeah.
That is a wild thought to leave on. Thank you so much for joining us on this incredibly detailed exploration. The next time you open your laptop and see that polished, simple desktop, don't take it for granted. I invite you to click around. Dig into your own configurations, peek at the legacy control panel, toggle a hidden file, and see the sprawling, hidden metropolis of architecture sitting right there in plain sight. Keep learning, keep exploring, and we will see you on the next deep dive.